Hello everyone, this is Team 33, and I'm Xie Jiachen. With me are Yang Ruichen, Chen Yuwei. Our topic is Mini Metro AI Agent. So our content is, well, firstly we'll introduce what Mini Metro is, what work has been done, how we collect our data, how we design our baseline agent, how we approach the problem, how we evaluate our matrix, and how we analyze our results, and finally GitHub link, references, and contribution. So what is Mini Metro? Well, Mini Metro is a game that allows players to design their own subway map via connecting lines and transporting passengers along the way. And try not to get stations overcrowded as time goes on, as passengers accumulate. Our goal is, of course, to design an RL agent that will transport as many passengers as possible, and if any station becomes overcrowded, the game will end. So for context, this is our in-game frame. As you can see on the top right corner, you can see how many passengers we've transported, and the little white pixels that are beside each station are the passengers, and on the top left, you can see a station that is already overcrowded. So this is a game's frame shortly before game over. Right. So formally, our problem statement is to design an RL agent that will play the Steam game Mini Metro, and then also survive as long as possible. Why is this important? We think that Mini Metro will reflect the complexity of real-world urban transportation planning, because Mini Metro strips away all these not that necessary factors out and only leaves the essential of how efficient is a line to let the user ponder. And our contribution is that we hope through some methods like OpenCV and integrated real-time frame classifiers to train an RL agent that would help in actual metro planning in reality. And what has been done? Well, there are a proxy called Serpent AI that allows users to communicate between games. So this proxy will return a game frame to the user, and after the user has processed it and given back to the proxy will perform the action for us in game. So the user only needs to handle how agent understands the environment and how agent responds to the environment. So of course, knowing that Serpent AI is so useful, we try to leverage the benefits that Serpent AI has provided us, but ultimately failed since the Serpent AI actually did not support anything up that is up higher than Python 3.6, which is already deprecated, and then it also has long execution time. For any program to run in Serpent AI, it costs around 5 minutes before any results appear at all. And then it has difficulty in merging the latest helper modules with the legacy system, mainly because there are some module version conflicts that needs fixing, and only one team member can actually run the Serpent AI because of microarchitecture issues. So in short, it was way too time consuming and inefficient. Well, so we had to start over from scratch. So our second approach is to use OpenCV. We tried to tackle classification methods of agents by trying to mask the game frame and extract the essentials. But well, that ultimately failed as well. But in the meanwhile, we tried masking and flood fill, and we'll demonstrate our results. So firstly, we tried to dilute the line mask and apply HSV gray mask to find contours in a white-only mask. And we'll detect stations based on how many contours it has. For example, a square station, it might have 4 contours, and so on so forth. But in our version 1, we found out that, well, it cannot accurately detect all of the stations and even circle some regions that are not remotely looks like a station. So we thought, well, let's just re-engineer how we apply the gray mask. So instead of a gray mask, we apply white rings in HSV and then find the stations in a white-only mask. And the results were a bit better, but still, it was not the accuracy that we desired. And so we skipped over to version 3 because we thought, well, the previous two versions were had over-engineered how we applied the line mask, so we ignore all of these and just apply a single white mask that catches all the stations with a minimum detector area of 150 pixels squared to filter out many little bits such as passengers. And but the result turned out to be not that satisfactory because it still circled something that is not station and has many misclassifications along the way. So we switched to flood fill. Firstly, our thought is, well, why not we flood the entire game frame and stop when we approach a black contour, because each station has a black contour. But that ultimately failed as well because the results, as you can see on the left hand side, has flooded the entire game frame with black, which rendered anything not possible to detect at all. So we switch over to flood fill, but only fill the parts that has color, and the right hand side is our result of version 2. While it is an improvement from all black, obviously, but still did not provide any useful insights into how we can isolate stations from game frames. Well, finally, we decided to switch over to the simplest classifier CNN models, and we found out a website called RoboFlow, which you can upload your annotated data and they will train the model for you. So we did exactly that. We annotated around 500 plus game frames and uploaded them to RoboFlow to train for line detectors and station detectors. And finally, we had an impressive results of lines over a precision of 80% and stations of precision over 98%. This is the visualization of our results. As you can see here, this is our line detectors, and the right hand side is our station detectors. Well, to summarize what we've done so far, we tried Serpent AI, OpenCV, and RoboFlow, and in which we failed to classify anything in Serpent AI, therefore its precision is none, and also because we use algorithm in OpenCV and Serpent AI to identify stations, so we do not require any data sets for these two methods, but instead we needed 500 plus annotated images for RoboFlow, but in return the precision is the highest and the implementation difficulty is the lowest because we only had to annotate images, which is time consuming but not that hard. Well, and then we'll move on to how we design our agent. We decided to use Dagger algorithm to train our RL agents by pre-processing the images from expert datasets to CNN and retrain our policy to refine our agent play logic. We use Steam to run the game, and how we collect our data is via a module in Serpent AI that allows us to screenshot a certain game frame every like 0.5 second and something, and then we annotate the data by hand using RoboFlow, and then upload that to RoboFlow and get the model. So this is our numerical training performance, and you can see the precision on the right hand side. And then we need a baseline agent for comparison, so we designed one, and how it works is that it only detects circles, squares, triangles in a game frame, and then connect stations whenever possible. Of course, it has a shitty performance and quickly runs out of line capacity and extend other stations afterwards, but still it's doable and it has some scores. And but our main approach is that this is our main approach of our RL agent, which consists of first perception, how the agent understands the world, and then action space, based on the information that the agent got, how it will take actions, and then the reward on which reflected on the actions that the agents took, and then finally the learning step. So for perception, we use the detectors for lines and stations, and then we also had a context classifier classifying whether it is in-game status, or we need to choose weekly rewards, or whether we are already dead. And we also used OpenCV and OCR methods to isolate game state information such as passenger throughputs and all that. And then we packed all of these information into a global dictionary called world to pass that over to action space. And how we do action space is that we first define macro definitions. That is, we think that actions is a combination of verbs, argument 1 and argument 2. And then we actually define action space by combining a verb with arguments to form PA action to reflect what to do in the current game environments that is considered as valid. So a example might be drag track from this segment to that station, right? And then after we have defined the action space, we'll return the actions to the agent action, which will do an action, of course, and then the game will change because the agent did something, and the agent has to perceive again, and then creates a new world variable, and then pass that over back to action space to recreate a whole new action space for that world. And then for actual action execution implementation, we'll first dissect PA action, find argument coordinates in the frame, find a final check on whether this action is valid, and then perform actions by PyAuto GUI. And then let's move on to reward. How to define and reward on actions? Because we only had detectors for lines and stations, so we will base our reward on that. So firstly is, of course, our passenger throughput, which is also the score we will assess for each gameplay. Of course, as high as possible, and asset usage, because we can only detect how the line is formed and not detect the passenger load on each lines, so we can only encourage the agent to use as many assets as possible. And then for line status, we value diversity, span, linearity, loops, and spatial coverage. And this is our main approach for agent learning. So firstly, we use expert dataset for warm-up, and then we use Dagger to pass the dataset in, and then let the agent play by itself. And then we intervene whenever necessary, and this will create another .json dataset to feed back into the Dagger algorithm, and then the entire process is a subset of supervised learning. This is the formal definition of how we approach our agent learning part. And we evaluate our metric by how the agent performs globally in terms of passenger throughput. But in the end, that failed because we had insufficient time for our approach 3. We spent way too much time in approach 1 and 2. And then for RL training, we failed to map user actions, expert actions, to action space, which in turn did not pass our actions into expert datasets, which cannot, so we cannot warm start our Dagger algorithm. So as a result, we did not have any expert dataset and did not yet perform RL training. So our future work might be, firstly, we'll fix user action to action space mapping, and then if everything runs correctly, we'll experiment with various RL methods and mod Minimetro so that our in-game environments better aligns with reality. And then we'll also experiment with higher precision agent that will be able to detect more stuff. And this is our reference and GitHub link. And this is our contribution. So in short, although not successful, we have fully implemented a a well, at least a skeleton for agents that will classify and understand how the game frame is done, and understands the game, and also take actions, and it realizes rewards. So actually this is just one step away from actual RL implementation, and we hope to refine on that and produce some actual results in the future. Thank you very much for listening, and I wish you a nice day.